Today we do this fiber products, dry fiber products, and then move to shifted symplectic. Okay, there is a remark. If I didn't put on blackboard last time, so remark is the following: the cohomology H dot of this tangent, relative tangent space. But dg tangent to space of Fn of shifted by -1 naturally a sheaf of graded the algebras, graded the algebra. This actually we did last time, and so if we row of the cochain complex, the role of the cochain complex of T dot at the point X. You should look at your notes for this notation. Shifted by -1 is being displayed by this formal ring, displayed by this formal rings of M. This is something we did last time, which is the completion of O dot of M. O dot. Completion of O dot along the subscheme X of N, where X was the map of here, which was a section of morphism between two schemes, M to N. So this is something we did last time. We discussed why this is, roughly speaking, this the algebra. Cochain complex. Okay, so now there is a theorem. Let us continue. There is a theorem that F from M to N, any morphism of quasi-projective schemes. The underlying schemes are projective. Then F can be factored as or through. So N goes to something with tilde, and then F tilde from where I is a quasi-isomorphism of the schemes, quasi-isomorphism embedding, and F tilde is smooth. Any two such factorizations give rise to, can be included in the third one. Included into a third one. So this is the fact that if I give you a DG scheme, can it have some smooth resolution? This is the statement. So the proof is again similar to before. Proof of this is the following. So we embed M0, which is the truncated part of the DG scheme M, into n0 times some p of n, then take n tilde 0 as an open set. An open set in. This is similar to the previous one where we were trying to, given a DG scheme, we knew that we can always embed it into a DG manifold. This we did. So this is almost safe. So M0 is that M0 is close to M bar 0 as an open set. And take M bar 0 as an open set in M0 times Pn such that M0 is closed in M bar 0. Then the procedure is similar to before, and for any closing point. So before we had this construction for any closing point, right? Before we had the construction where I give you a DG scheme M, can I embed it into a DG manifold? And now we have a morphism of DG schemes M to N, and we are trying to save all these factors to a smooth morphism of DG manifolds. The only difference here is that N is a so a diagram M goes to this guy M tilde goes to this guy N. Oh, N, sorry, N will be called a smooth resolution of F from original M to N. It is not injection. So now we also have the relative version of this construction. So there is a proposition. Sometimes is a corollary, but I stated as a proposition. This is the relative version that says let F be a morphism of N schemes, so DGS schemes. So let's say F is a morphism from so let's write it that. Let us consider a morphism of two DG schemes M1, M2 over some given DG scheme N. So let's call them F1 and F2. Let's say this is a commutative diagram. So consider this to be a commutative triangle with f of I smooth and Q a quasi isomorphism of DG schemes. Then P of Q is the morphism in the level of the DG tangent sheaves, map M1 over N, tangent sheaf of M1 over M, to pull back of the DG tangent sheaf of M2 over N. And there is also N, via this you can pull back things, which will be dually. It can take you from sheaf of DG sheaf of relative differentials of M2 over N to sheaf of relative differentials of M1 over N. Okay? Both of these morphisms are quasi-isomorphisms. Like this, and these are smooth, you can think of this as the DG version of diffeomorphisms. Think about diffeomorphisms. Two. So if the morphism is smooth, what it means is that the cone of that morphism, if the morphism of this smooth in the level of sheaf of first order sheaf of differentials, scalar differentials, or in the level of tangent, DG tangent sheaf, the cone of that thing will see nothing. That's why we get a quasi-isomorphism. Okay, so definition, the derived relative tangent complex of a morphism F from M to N of quasi-projective DG schemes. Is, by definition, basically the derived tangent, DG tangent sheaf of M over N. And I would like to say, what is the derived DG tangent sheaf mean? Well, by definition, the derived DG tangent sheaf of M over N is the DG tangent sheaf of the resolution of M over N. This is why we need the resolutions. Okay? So every morphism will have a resolution. That's what it is. Where S tilde from M tilde to N is any smooth resolution of F. This is DG sheaf of algebras. This is a sheaf of DG algebras. DG the algebras. The algebras on M tilde. Of course, it is true. What the derived tangent complex is. These are already complexes. If your DG scheme is just smooth, you just use the sheaf of differentials to play the model for the derived cotangent complex. Dual of the sheaf of differential is the tangent complex, which will be otherwise reusable. Also, the same thing, by the way, is the case over derived schemes and derived stacks, not necessarily just DG, but derived stacks in general. So, example, let M equal to X be a C point of a DG scheme at K. The morphism is that point. So the C point of the N. Then the derived relative tangent complex in R of the derived DG tangent sheet of X rounded to N is quasi-isomorphic to E dot at point X of N shifted by -1. So how do we see it? To see this, let M tilde be the spectrum of the K dot of over X. K dot of over X. This is the Koszul resolution. Koszul resolution of the vector space which is supported on that point X inside the DG schema. Okay, this is the Koszul resolution. And this plays the role of this affine DG scheme. So let this be the spectrum of that on an affine DG submanifold U, which is a submanifold of N containing X in N. Then that actually gives you this. You always need to have some smooth manifold. The spectrum of the Koszul resolution of this guy gives you that. Think about, compare this with the statement that we had before, that the completion of our structure ring at that point also gives you the solution. So this point, the formal ring of N at that point, completion of the formal ring gives you actually this basically gives you the Cotangent complex for that. That's that. Now, we also need fiber products and derived fiber products for applications that you will soon see, probably today. So let's talk about a little bit of those things. So derived fiber products. So this up to there was finishing the material that we covered last time about tangent complex and cotangent complex, the tangent DG sheaf and cotangent DG sheaf of DG sheaf. So let's talk about fiber products as well. So let f of I from mi n be morphisms of DG schemes, for I1 and 2. The fibered product, and 1 over n times n2 is defined as follows. First, form the fibered product of underlying the schemes. We'll truncate the scheme. So you have something that you have DG schemes, and their structure ring or structure DG algebra is given by this CDGA, commutative differential algebra, and you look at the A0. So the underlying schemes are given as the schemes over A0, like what we had last time. So we have these things. Okay. And then we can map this to this. One. And these two things are F2 0 and F1 0 going to N0. Whenever you have a morphism of DG schemes, you have these morphisms. And then define M1 over N times M2, the fiber product to be the information of M01 times M02 over N0 together with the algebra. So this is G2 comma 0 minus 1 of O dot of M2 times G1 comma 0 inverse of O dot of M1. And the tensor product is over, so this is over F1 comma 0 O G2 are composed with G1 comma 0. This is over this thing. Okay. There's something I wanted to mention here. Just remembered.
The notation here, G2 comma 0 is just to show that these are acting on superutilized schemes.
That's right. Yeah. Well, that's right. I mean, acting, well, you can think of it as an action, but there are more underlying schemes. That's right. But there's something I wanted to see. Okay, never mind. I mean, I've forgotten where it is. Okay. Probably comes back to me. Okay, so you have this. Now, proposition if F2 is a smooth morphism, then so is G1. More precisely, let F from M to N be a morphism. And Y some, C point of N, for instance. Okay? Be a point. Yeah. C point. I guess we are assuming that we are working over C, but any field of characteristic 0 works. So the fiber F inverse of this point Y is the fiber product M times Y over N. Of course. Now if F is smooth morphism, then F inverse of Y is a DG manifold. Moreover, if M, N, and F are always smooth, then we have then we have the following. So there is this map. Let's call it kappa from tangent sheaf at y, DG tangent sheaf, DG tangent space, I'm sorry, at y of n shifted by -1 to the derived sections of f inverse of y tangent to space of f inverse of y, which is obtained from as soon as I put it, you will see that this is familiar to you. This is obtained from 0, the exact sequence of tangent sheaf. So 0 goes to t dot of m over n, and that goes to t dot of m, and then goes to the pullback of the t dot of n, and then goes to 0. So this is obtained from here by tensoring over algebra, DG algebra of M with O dot of F inverse of Y and using a junction. Okay. This guy is the one that sees the relative tangent sheaf. You have the relative tangent sheaf of M over N, but really, the tangent space of this one lives in here, right? So because you fix a point on N. Tangent space of the fibers. So that is that. Now definition. This was the fiber product of two DG schemes. Okay. Now definition. The derived fiber product, it's written like this. Derived fiber product of M and M1 and M2. Well, can you guess how it is defined? How is the derived fiber product defined? Now we know that we have the fiber product of two DG schemes. It is a DG scheme. Its underlying structure is that it has an underlying scheme, which is given by the fiber product of the underlying DG schemes, and then some algebra which you can construct by tensoring the algebra. So what is your guess for the derived fiber product? What was the derived morphism? Or derived derived tangent sheaf. The derived tangent sheaf was the tangent sheaf of the resolution, right? So when you take the derived fiber product of two schemes, one of them needs to be replaced by its resolution. And in the world of DG schemes, we can always have a resolution. The derived fiber product of these two is defined as M1 tilde fiber product with M2, where F tilde from M1 tilde to actually to N is a smooth resolution of F from M to N. Now, so there is a lemma that the definition of M1 derived fiber product over N with M2 is independent up to quasi-isomorphism. Up to quasi-isomorphism of the choice of resolution.
Is the morphism right half for the isomorphism?
No.
No.
But as long as your resolutions are quasi-isomorphic, your fiber product is the same. The derived fiber products are the same. But this is a lemma. Okay, so I say more. So basically, to prove it, with this suffices to show that given two smooth resolutions, for instance, of F, let's call them like this. Remember that this was M1 prime, for instance. Okay, so remember that this was M1. This is your F, and the idea was that your map always factors through a smooth resolution. Those are okay. So it suffices to show with let's call this thing Q or G, with Q quasi-isomorphism, the induced morphism M1 times M2 over N to M1 prime times N2 over N. I have some typos in my note. N2 over N is a quasi-isomorphism. So how do you prove that? For this, we have this thing that we defined before, the Eilenberg-Mort spectral sequence. So for this, we show the ladder, we show have a morphism from Eilenberg Moore spectral sequence calculating homology of the algebra, DG algebra of M1 tilde times M2 over N. And we get a morphism from the Eilenberg-Moore spectral sequence that calculates this one to the Eilenberg. So how do I write it? To the similar Eilenberg-Moore spectral sequence that calculates cohomology of, well, the other one, O dot of M prime tilde times M2 over N. Okay. And this morphism is an isomorphism, isom on E2 pages. This is roughly how the proof goes. Or in two terms. In two terms. It's a little bit involved, but you can find it in the paper of in the notes of Toan, you can find it, I'm sure. Where we are using this from, this is the paper of Kapranov. They haven't proved it, but you can find it in Toan's notes. Anyways, I think it's better that I make an example rather. Okay, so this derived fiber product is by replacing one of the DG schemes with this resolution, and it's independent of quasi-isomorphism of the course of resolution. Okay. So let's see. Let us make an example. Derived intersections. Derived intersection. This is a good example. Let if y and z are closed subschemes, of a quasi-projective DG scheme, let's say X, then the derived intersection they write it often like Y derived intersection with Z is defined as the derived fiber product. Derived fiber product of Y and Z over X. Via the natural embeddings. These are DG subschemes, so via the natural embeddings of these. So these are two DG subschemes. closed subschemes of DGC. Okay, if X and Y and Z are ordinary schemes, then the homology sheaves of the DG algebra of the derived intersection of Y and Z inside X are the tor I over OX modules OY comma OZ sheaves. You have two subschemes in an ambient scheme. They are intersecting. If they are intersecting transversely, tor 0 of this is just a normal intersection of the algebra of these two things. So this gives you the intersection of Y and Z, the ring of functions on the intersection of Y and Z. So if they are transversely intersecting, all higher tors starting from tor 1 vanish. But if they are non-transversely intersecting, then you have all of the higher tor sheaves. Now the DG algebra of the derived intersection of Y and Z actually has homology sheaves, and those are given by the tors. So this is essentially the message we were trying to convey from the beginning of the class, that now we are, via this language of resolutions, we are trying to construct a geometric object in a different category that understands non-transversality geometrically, but not just as cohomology classes. You're constructing a ring, but it's a DG ring, so I can take its cohomology. And the cohomology of this ring of functions on the DG scheme in a DG sense, captures exactly the cohomological data that we had before. So this is essentially the application of derived geometry. Okay. But so far, all the complications, so in some sense, so far, I haven't yet convinced you why doing derived geometry is useful, right? Except I've just told you that we can construct spaces which are rather geometric but contain cohomological data. Okay? But you could say in regular, usual classical algebraic geometry, we can just calculate these cohomological data. So it seems like if I have a difficulty in calculating those cohomology classes, there are same difficulty exists in here. If not, this is also very doable. That's right. So far, we are just basically making the parity between this language and that language. They are so far equivalent. So, but derived geometry has advantages over regular algebraic geometry. You will see as soon as we move to the language of shifted symplectic structures. Okay, so that is that. Now, good. So now, let's talk about those things. So I think we have now enough ingredients to talk about shifted symplectic structures. Okay. So let me actually remind you, first some reminders. So this was a definition that we had before. Write derived stacks over C for the infinity category of derived C stacks. So this is the object that we constructed before over the category of simplicial rings, okay, over C, or sometimes sometimes they call it D minus stacks. But anyways, so objects in this category are infinity functors. Infinity functors means that we have the objects, morphisms between objects, morphisms of morphisms, and so on and so forth. So infinity functors from X, which is the category of simplicial commutative C algebras. This is exactly what we started the class with, to the category of simplicial sets. So these are the same thing. In fact, we constructed a pre-sheaf of taking values in simplicial sets over the category of simplicial commutative algebras. And then from that, define the notion of stacks and schemes, algebraic stacks, things like that. So this is our notation for what we had before. Okay. So, and this was satisfying certain sheaf conditions. We needed to define the notion of sieves and so on, and we needed to define the notion of hypercovers, and our pre-sheaf of simplicial sets needed to be compatible with respect to hypercovers, satisfying the sheaf conditions. Okay, so this is what we had before. Now, let's also remind yourself that we had this notion of a stack from the opposite CDGA to this category. So this is was the spectrum functor. Okay, so for every commutative differential integrated algebra, we can define an affine scheme over that CDGA, which is also an element of the bigger category of derived stacks. Okay, so a derived C stack X tilde is called an affine derived C scheme if X tilde is equivalent to a spec of some A dot for some CDGA A dot over C. This is in some sense the summary of all the things we did. Okay. Now, this is the derived affine or affine derived C scheme. Remark. A derived stack X tilde is called a derived scheme, a derived C scheme, if it can be covered, by Zariski open Y tilde inside X tilde with Y tilde derived affine schemes. Also, this we had before when we were discussing the Zariski open morphisms. We had this guy before. And we in fact had this notion somewhere that I defined for you an element of this stack, and then I called the scheme if it could be basically covered by these kind of things. So just look at the earlier notes. And, okay. So now we use the notation. We use the notation. So this is actually telling us that derived affine schemes over C are a full subcategory of derived schemes over C, which itself is a full subcategory of derived stacks over C. Okay. We assume from now on, that all derived schemes are finitely presented. This induces strong conditions on the cotangent complex of these schemes. It makes the cotangent complex a perfect object. And by requiring it to be perfect. Meaning that every time that you cover your scheme by derived affine schemes, those are your local charts, the description of your cotangent complex must be as an algebra over that underlying CDGA of that affine chart should be finitely many copies of that algebra, probably with different shifts. So that is what makes a cotangent complex a perfect object. It needs to have finitely many terms, and locally these should be modules over underlying algebra. So locally you look at your derived scheme with covered with some derived affine schemes. On each patch, this guy should give you a perfect complex of modules over the underlying CDGA of that affine patch. So being finitely presented means this. It is a strong condition. Okay. Recall that given any x tilde in this category of derived schemes over C, we had a truncation. From the category of derived schemes over C to the category of only regular schemes over C. That's our truncation T0. Okay. So also when we were discussing DG schemes, we actually discussed this truncation map. So if this derived scheme is itself an affine derived scheme over C, so it's the spectrum of some CDGA, then T0 takes it, so this is our X, the spectrum of A dot, to spectrum of H0 of A dot. This also we discussed when we were in that room. And so what is this? This is the spectrum of A0 divided by D of A minus 1. This is the truncation. This is our So what is actually what we've done? We've constructed these derived stacks formally, functorially, and categorically. And the idea is that the ones we care about are coverable by derived schemes, coverable by derived schemes over the category of CDGAs. So all of the ones that we work with locally look like DG schemes. All of our derived stacks, the derived schemes, locally look like DG schemes. Okay. So given X tilde in the category of derived schemes over C, let L dot of X tilde be the cotangent complex
I have a naive question. For schemes, if you just know it's a standard represented,
Yeah.
then it's a cotangent complex in the sense of use in general it could be very bad, not perfect. And so what happens here that makes things so good for derived schemes, DG schemes? But once you impose condition is finally presented, then it's a cotangent complex becomes perfect. What makes such a big difference?
No, I mean, locally it will be a perfect thing. That's what I'm saying. Locally finite
The same
represented.
statement for scheme is not correct.
No. Yeah, no, it's correct. Yes. Why not?
In general scheme, if you take the cotangent complex and just what is
So let me define the notion of perfectness in here, and then I will tell you. Give me a second. Actually, I'm going to talk about it. No, actually, this. Okay. So it's a matter of difference of notation. So here also our cotangent complex is for a DG scheme going to be unbounded. It's going to be only bounded from one direction. Always perfect from one direction and not the other direction. So for the question that you're talking about, for our scheme theory, for just the usual scheme, okay, our cotangent complex will be bounded from above, doesn't have terms of degree more than one probably, but it will be unbounded in the other direction. But let me show you. Okay. So actually I'm going to right now I'm actually going to talk about it. So cotangent complex of a CDGA. So these CDGAs are going to be giving us the local affine charts for our derived schemes, right? So let's first talk about those. So define A dot and D CDGA with this differential. Then, as we saw, we have the module of Taylor differentials over A dot, which we called it omega dot 1 A dot with universal degree zero derivation. Delta A dot goes to omega dot 1 over A dot. And we also have the Durham algebra of A. So, and the Durham algebra of A dot, which is simply given by the Derived algebra of A dot is defined as symmetric algebra over A dot of this guy shifted by 1. With degree minus 1 Derived differential. So remember that now we are talking about Derived algebra. For every DG commutative ring, differentially graded commutative ring, we have this internal differential goes like that. All right. So for each one of these things, now we can construct a Derived complex for each term. We can construct a Derived complex by derivations. And so you also have the Derived differential that takes you from whatever copies of omega to the second symmetric algebra, third symmetric algebra. So that's the Derived differential. Okay. So that one has degree minus 1. So the Derived is taking us from here to here. Okay. Yeah. So 2 forms are sitting in degree shifted by 2, 3 forms are sitting in degree shifted by 3, and so on. The differential D on A dot induces a unique differential on omega dot 1 over A dot. That's the DG cotangent sheaf satisfying dO delta equal to delta OD, which takes you from A dot to omega dot over A dot. So this is exactly what I put in here. Call one of them D, the other one derivation delta, and so it satisfies this commutativity. So okay, that we know, and then this makes omega dot 1 over A dot, this differential into a DG module over A dot. These are things that you have seen before. Okay. All right. So now this is the point that we are trying to say. When A dot D is nice enough, is sufficiently nice, then this guy, this A dot module, DG cotangent module, together with its uniquely defined differential, which comes from this construction, is the model for cotangent complex. Cotangent complex, which we can denote by L dot of A dot. this is kind of almost trivial statement. If you have some commutative CDGA, the spectrum of that thing is a smooth thing, and its cotangent complex is the same as its shift of differential. So this is that statement. And the cotangent complex completely is captured by the DG cotangent shift. So, moreover, given a morphism of CDGAs, A dot to B dot, then we can define as before. We can define as before. The sheaf of DG cotangent sheaf of B dot over A dot, which gives a model for the relative cotangent complex of B dot over A dot. Okay. So we are reminding ourselves of these things because we would like to cover these DG schemes locally with affine DG schemes, and affine DG schemes have these kind of properties.
Is there notation L0 or L dot?
L dot, I'm sorry. Point is, if I'm looking at only a CDGA A dot, cotangent complex of it, you always think about its scalar differential. That's it. Together with its differential, defined by A.
Previously, you said when the derived scheme finitely presented, then it's perfect. Do you mean the truncation?
Truncation is perfect.
Truncation and greater than 0.
Truncation, it's truncated for degrees greater than 0. And actually, we will talk about that right now. So, some properties. I think, given some map of this via this definition, map of DGRs, commutative DGAs, then you always have, then this induces a triangle L dot cancel over A dot with B dot goes to L dot of B dot goes to L dot of B dot over A dot. This is the exact triangle of cotangent complexes, which we have seen before. 2, given a homotopy push out, of CDGAs. Let's say A goes to A prime, then goes to B, then goes to B prime, something like that. You always have this base change. You have that this induces a base change. So base change L dot of B prime over A prime with the dots is going to be quasi-isomorphic to L dot of B dot over A dot tensor over B dot with B prime dot. So that is the base change. So I think these are the properties that we want. Now, note that, so these are the properties we want. So now I can move to derive the steps or schemes. So how much time do I have? 15 minutes is it? Now, given this, let's talk about cotangent complex of derived schemes and the stats. So now we know what the cotangent complex locally, what properties it has. So these properties carry over derived scheme and the stats. So let X tilde be in the category of derived stacks over C. In usual geometry, its cotangent complex L dot of X, and dot of X is an object in the derived category of quasi-coherent sheaves on X. In derived geometry, so here, where X is the truncation of X tilde. In derived geometry, it lies in some different kind of derived category. It's called L quasi-coherent of X tilde, which is defined by Toen. So let me say some things about this derived category. This is which is a generalization of the derived category of quasi-coherent sheaves on X with the following properties. What are the properties of this? Almost everything carries over. So one, if X tilde is a derived stack, and L quasi-coherent of X tilde is a pre-triangulated category with a T structure whose heart is the abelian category of the quasi-coherent sheaves on the truncation, zero truncation, or underlying scheme of the derived scheme X, or derived stack X. Okay. In particular, if under the embedding of category of schemes over C to category of derived schemes over C, X tilde is I of X for some X. It's a, oh, by the way, maybe schemes or stacks. So stacks over C, derived stacks over C. Or if X is a classical C scheme or a stack, it is a classical T-scheme for a stack, and classical C-scheme for a stack, then this category is the same as the derived category of quasi-coherent sheaves on T0 of X. Okay. So please note one thing, that this is also something we discussed in the CTGA and the DG schemes, that the truncation of a, even if you're giving me a DG scheme, so you have a derived scheme, it's locally covered by DG schemes. Remember that this truncation of the, even the truncation of a DG scheme is not a scheme over a spectrum of the A0 part. You look at the algebra and you look at the cohomology, so there's also always A0 divided by image of A minus 1, so it is different. Okay. So this we have emphasized multiple times. Okay, so you have that. Now, inside this category, which is some kind of derived augmentation, derived enhancement of the derived category of the scheme, if you have some morphism between derived schemes, again, then you have the notion of pullback from the derived category of the affine derived scheme Y, the derived category of the derived scheme X. And part 3, if some A dot is a CDGA over C, and X tilde is spectrum of this CDGA, so it's a DG, it's a DG scheme or a derived affine scheme, then L quasi-coherent of X tilde as a category is equivalent to category of DG modules, DG A dot modules. A dot modules. Okay. In contrast, though, I write this in red. In contrast, maybe yellow. The derived category of quasi-coherent sheaves on the derived scheme is the derived category of modules over H0 of A dot. Again, it keeps coming back that there is a difference between a spectrum of A0 and the spectrum of H0 of A dot. This keeps coming back, right? Which depends on T0 of X tilde, which is equal to X. Okay, so that's that. So what else? Okay, only 6 minutes. So I think to fix the sentence that you mentioned over there, we need to somehow clarify perfectness, right? So often perfectness is given as a amplitude. So your cotangent complex could be perfect from amplitude minus infinity to 0, minus infinity to 1, and so on and so forth. So that's what we need. So when we say perfect, it could be perfect from one direction and non-perfect from the other direction. But when, I think I should have said perfect from one direction, not having any higher homologies in the positive degree. I mean, you even have this notion of non-perfectness of, for schemes, for instance. I mean, we will discuss about deformations of abstraction theories. We need the notion of perfectness in this sense. We call this perfect. Of course, you can have some different complex which is perfect in this amplitude, but we will not, depending on what context we're talking about, we will not call this a perfect complex, because it has one degree more. So I think I should have mentioned which amplitude. If your scheme is just a derived, a smooth affine scheme, this cotangent complex is just perfect. Let's just accept that. Otherwise, yes, it could have infinite resolutions. Okay. So, so I think all of the properties that we almost have seen before do carry over here. So I wonder how many of these things should I really put in here. So let me just say something. I mean, majority of these properties carry over. Exact triangles do carry over. Push-outs also do carry overs, exactly like CDGAs. But this is what I would like to say. So now let's talk about the following and then finish and continue last time. Next time. Let X be a classical smooth C scheme. Okay. Then it's tangent and then it's tangent and cotangent complexes are vector bundles. Right? If it is a classical smooth scheme, which we call T of X and T dual of X, right? Okay. Now, on a classical smooth scheme, we can define a notion of a P-form. So a P-form on X is a global section W of Pth exterior algebra of cotangent bundle. This is something that we have seen from manifolds theory. Okay. So I tell you a point of view about this, and then we continue next time to shifted symplectic forms and things like that. So there is a Derham differential P Derham, which sends you from lambda p of the cotangent bundle of this smooth scheme to lambda p plus 1 of this cotangent bundle. This is a Derham differential, right? Which is a morphism of sheaves of vector spaces. And not sheaves of OS modules. Okay, no problem. And it induces a morphism. So D Derham induces a morphism from H0 of lambda P of the cotangent bundle to H0 of lambda P plus 1 of the cotangent bundle. Okay? Now, okay, a closed form P form. P form omega is some element of H0 of lambda P of the cotangent bundle, such that under this morphism it vanishes, right? Such that with d dirham of omega equal to 0. So this is what a closed form is. Okay. Now there is this interesting point of view. Also, okay, furthermore, a symplectic form on X is a closed two form omega such that the induced morphism under truncation along the vector fields, this induced morphism is an isomorphism. Okay. Now, before going to the closed forms on derived schemes, and what we are trying to do is that we would like to, this is a classical smoother scheme. We would like to look at the derived scheme, then define the P forms on the derived schemes and the notion of closed P forms on the derived scheme. And that will be something that induces maybe not isomorphism, but some quasi-isomorphism between cotangent complex and tangent complex of the derived scheme, probably with some shift. And basically that is going to be the shifted symplectic structure that we are talking about. Now, note the following that, oh, how much time do I have? No, almost over time. Okay. Before going to shifted symplectic structures, first we think of this closed forms as functions on the loop stack of a scheme. We describe a scheme and we construct this loop stack of the scheme, and then our forms will be certain forms on the loop stack. On the classical scheme unit, we are trying to say that the P forms are going to be functions on some certain object, the loop stack, and we map from circles to this classical scheme of given weight P. And then the closed forms or the closed P forms will be functions on the loop stack of given weight P, which are going to be somehow equivariant with respect to an action of a rotation of a circle. So this is our point of view. As soon as we can fit this point of view for the classical C schemes, then all we need to do is to just write down the generalization of it for the derived scheme. This is what we are going to do. Okay, let's do it next time. We start from here. Again, I will talk about P forms and then loop stacks and then closed forms using loop stacks. Still on these schemes. I just want to emphasize we are still doing the schemes, usual schemes. We need the loop stacks for the usual schemes first, and then we go to derived schemes. Okay.